Log on, tune in, find out. Another good idea from Cambridge.
Random walks and jump processes.
Thank you very much, and also for invitation. So, in fact, I start with history of this subject, which actually goes back to geometry of Riemannian manifolds. Somehow, from the point of view that I will use here, the subject of stochastic completeness was first addressed in Riemannian geometry. So maybe it's a little bit away from the mainstream of this project, but nevertheless it's interesting by itself, and then there will be some interesting comparison between what's happening on manifolds and graphs. So we'll look at Riemannian manifold, so far arbitrary, maybe connected, M Riemannian manifold, and we'll look at Brownian motion on M. So I'll denote it by xt. T is continuous time, Brownian motion. This is just diffusion process which is generated by the Laplace-Beltrami operator. In principle, if someone is not familiar with this subject, you can just imagine some curved surface and random process, random movement on this surface, where each time when particle arrives at certain position, it chooses next all directions in the tangent space equally with equal probabilities, and then moves along one of these directions. Somehow the process sees geometry of the manifold in the way that it chooses uniform direction with respect to tangent space. So it goes like that. So analytically, one defines this by using Laplace-Beltrami operator and the associated heat semigroup. And then one can define transition densities for this process as the fundamental solution of the corresponding heat equation, and using transition densities can actually construct this process. So position at time t will be denoted by xt. There is some fixed x0 initial position of this process. For example, particular case of this construction is classical Brownian motion in Rn. Right? So what is, there are many questions one can ask about such process. One of them, very basic from the point of view of probability theory, if the lifetime of this process is infinity. The process is called stochastically complete. If its lifetime is infinity with probability 1, or almost sure. So what it means? How lifetime can be not infinity, finite? Well, this means that the process is well defined for all positive values of t. Right? How that can happen otherwise? It's very easy to see. Take M as just domain in Rn. Suppose M is some, say, bounded open set in Rn. Then the process will be just process in Euclidean Brownian motion, but when it reaches the boundary, it actually stops at the boundary. It gets killed at the boundary. In this case, lifetime will be finite. As soon as it reaches the boundary, it stops existing, and its lifetime is finite. That's how stochastic incompleteness can happen. This is example of stochastic incompleteness. Here, in this case, of course, this has to do with certain killing condition. Whenever you have certain killing condition for the process, it will stop existing at finite time. But interesting, of course, is not that. Interesting is whether stochastic incompleteness can happen without killing condition. That was really first realized by Azenkot in 74, when he constructed example of geodesically complete manifold. Complete but stochastically incomplete manifold. When I say stochastically incomplete manifold, I mean stochastic manifold with stochastically incomplete Brownian motion, right? Just to simplify terminology. Geodesical completeness means that geodesic rays, which start at any point, continue to infinity. In this case, of course, this ball or whatever we have here is geodesically incomplete. And if we have manifold which is geodesically complete, then there are no explicit killing conditions, right? No boundary where one can arrive at finite time. But nevertheless, lifetime on this manifold happens to be finite. So what happens? Why is the case? Turns out, to understand that, just maybe let us just speak a little bit how Brownian motion actually moves in Euclidean space, for example. If you are observer, you stay at one place and watch from distance what's happening with Brownian motion. So you are at the origin, say x naught, and see what happens to Brownian motion. Right? If you are in Euclidean space, basically you will be turning all the way around you all the time just to keep watch in the direction of Brownian motion. It rotates mostly. Rotates like that, and very slowly goes away. It's known that its distance from xt to the origin, let me write mod xt, is roughly speaking square root of t, right? So it's very slow. But it's not always the case like that on other manifolds. If you look at hyperbolic plane or hyperbolic space, Hn, this is space with constant negative curvature. Sectional curvature is constant -1. Then the picture is different. The picture is like that. Maybe I'll draw this space. This is also geodesically complete. But then when Brownian motion starts moving, it fluctuates, but then chooses certain direction and goes away almost along geodesic. So basically, after a little rotations, you will be stabilized and look always in the same direction, right? And moreover, its speed becomes linear. So mod s, if we mean by that distance to the origin, is of order of t. And this is effect of negative curvature. Negative curvature accelerates Brownian motion, so it becomes quite fast, going straight to infinity. It more or less reminds this situation when Brownian motion reaches some point at the boundary. It also near this place, it goes more or less straightforwardly to that boundary, right? And this goes to the boundary at infinity along the geodesic ray. But then what Azenkot did, he constructed manifold where curvature becomes very negative. It's variable negative curvature which goes to negative infinity. And due to that, Brownian motion accelerates that fast that in finite time it covers infinite distance. Obviously, one can imagine deterministic movement. One can easily compute the law of that movement, that in finite time one can cover infinite distance. It's exactly the same happens with Brownian motion. On manifolds with very negative curvature, its behavior becomes practically deterministic. And it goes along almost geodesics to infinity in finite time. So the reason why lifetime becomes finite is not killing conditions, but it's just too fast. This is incredible because in Euclidean space, our ideas about Brownian motion it's something erratic, slow, going here and there, whereas on manifolds like that, the picture is entirely different. It's faster than light, right, one could say. Right, so that's quite weird, but nevertheless, this is effect of negative, very high negative curvature. Right, so that's effect that I'm going to discuss also for other processes, for jump processes, and also for random walks then. So what is known about positive results? Positive results, I state one old theorem which was proved by many authors, including myself in 80s. So assume that manifold is geodesically complete. From now on, M is geodesically complete, and denote by say V X R Riemannian volume of geodesic ball of radius r centered at point X. This is volume function of balls. In Euclidean space, this is r to power n. In hyperbolic space, it's practically exponential function of r. And on the space which Eisenkot constructed, it's quadratic or more quadratic exponential. So the positive result is as follows. If for some point x naught, this volume admits the following bound: exponential c times r squared for large enough r's, say, then M is stochastically complete. So this, one can slightly improve this, adding log r here. Maybe I'll just add log r. One can also add log r or write Dini type test, but it's sufficient for us to have it in this form. On example of Eisenkot, volume growth is actually CR2 plus epsilon. So it's much faster than.
So the 2 is sharp, in other words.
So 2 is sharp, yeah. Right. Actually, there is very sharp condition for that. The sharp condition for volume would be log volume test. Right. This integral must be, if this integral is divergent, then there is stochastic completeness. If for some function v integral is convergent, then one can construct manifold with this volume function, which is stochastically incomplete. So in terms of volume, this is a sharp test. Right, so Eisenkot test, Eisenkot manifold was that, but in fact one can get here, for example, log to 1 plus epsilon and things like that. So, right, so that is the picture, what one should know with respect to this talk about the history of this subject. Maybe before I go further, one remark, why it's still possible to say something in terms of volume. In some sense, curvature is intuitively more suited to describing behavior of Brownian motion. The point is that in terms of curvature, one can write more or less explicitly the integral or differential equation for the radial process, for distance of xt to the origin, right? If one writes this using Ito formula, then there will be some curvature there involved, and one can analyze really point-wise behavior of this process and then derive global information. Volume, of course, is not that precise information, but nevertheless happens that this quite rough information, this just general volume of balls, still gets you the same thing in the end. If you think a little bit, if you look at the definition of stochastic completeness and the Brownian motion, in fact, distance function is not used here at all, right? What one actually uses in this definition, one can use generator of this process, Laplace operator, and one uses, in fact, volume. It's hidden. Volume is hidden in the definitions of Laplace operator, in fact. Riemannian structure is used, but distance function is not involved at all here. Why distance function can be still used to say something about stochastic completeness, right? And distance function, of course, is needed here to define the balls. Why Brownian motion sees the balls? Right? The point is that this distance is geodesic distance. I said geodesic balls, it means let us denote dxy, geodesic distance. And balls are defined with respect to this distance. And this geodesic distance, of course, is defined by using the underlying Riemannian structure. And this somehow it's related also to everything else which is going on Riemannian manifold. But in this situation, one can actually say exactly what is used, what information about distance function is used to control the behavior of Brownian motion. In fact, the only thing one needs is that gradient of distance function is bounded by 1, model gradient. Gradient is Riemannian 1, so it's very much linked to definition of Brownian motion, and mod of gradient is bounded by 1. In fact, if in the domain where distance function is smooth, mod of gradient is exactly equal to 1. But in some weak sense, it doesn't have to be smooth always. In weak sense, it's always true. And this turns out to be of crucial importance. Moreover, one can replace geodesic distance by any other distance. I remove the word geodesic and say let dxy be any distance function with this condition. For example, it could be so-called extrinsic distance function. If one places given manifold in some ambient manifold and take geodesic distance from the ambient manifold, then one still can use that one, satisfying this condition. Right? But it doesn't matter where this function comes from. As soon as it satisfies this condition, this volume test will be true, and provided we define balls with respect to this distance. So that's important observation, because I'm going to use this for jump processes. It will look different.
So, sorry, can you repeat that again? So indeed, when the curvature is negative and D is always smooth, so that is satisfied. So, but
yeah, then grad D is 1.
what is the claim that when the grad D is more or equal to 1, then this volume test is always satisfied?
Yeah, I'm saying that if it's not necessarily geodesic distance, I mean this theorem is true, not volume test.
Okay.
Yeah, this theorem
applies.
Right. Yeah, this theorem applies with any distance, assuming that, of course, both are defined with respect to this distance, right?
And Brownian motion is defined with respect to that distance?
No. Brownian motion is defined independently. Brownian motion is defined by using Riemannian structure as before, right? Distance is introduced here independently of Brownian motion, but in order to make sense of that, one needs some relation between distance and underlying geometric structure, and this relation is given by this. Assuming that D is any distance with this property, and both are defined to be just with respect to this distance, right? The usual metric
volume is the Riemannian.
A volume is Riemannian. Volume is still Riemannian, yeah. So distance function plays some distinguished role. We take it out of Riemannian context, keep everything else, but the distance can be defined separately. Anyway, that's I was trying to say to explain why Brownian motion sees the ball, right? The reason is that the distance function somehow is adapted to Riemannian structure and therefore to this process. Right, so that is history of Riemannian manifold, but the main part of this talk is actually about jump processes and in particular about random walks on graphs. So I will go first to general jump processes. So the process that we discuss now, this diffusion process, is process with continuous paths. That's in probability theory. One distinguishes process with continuous paths and process with discontinuous paths. So these are diffusions, and maybe I should say one important thing also, that definition of this process can be actually done by using general scheme when one starts with energy integral. The classical energy integral in Rn is grad f squared dx, right? And it's related to Laplace operator. It's generator of this quadratic form is Laplace operator, and then there is a general procedure how to, starting with this energy form, define the process. So on arbitrary manifold, one would get the same by replacing integration with respect to volume and having grad f Riemannian. That's one of the reasons why here grad d appears. In fact, this notion, modulus of gradient, is in fact sits at the very core of definition of analytic definition of Brownian motion. Right. So, but then what I will be doing now, I will use different Dirichlet form and to define jump processes. And this also standard procedure, which is part of the general theory of Dirichlet form. In particular, this there is comprehensive source for this, the book by Fukushima on Dirichlet forms, where this approach is defined in all details, right? But I will try to be down to earth and avoid technicalities and generalities. So we'll look now at metric space. And D is a metric space which is locally compact and separable. And we are going to have measure mu. This analogous of volume, right? This should be a Radon measure. That is Borel measure, which is finite on compacts, and other Borel sets can be approximated from inside by compact sets. Radon measure with full support. That's kind of generalization of manifold. Every manifold has geodesic distance, Riemannian manifold, and Riemannian volume, right? And this is more general object where one can actually live. And we are going to consider jump process on this space with which in jump density will be given, or jump intensity will be given by some function jxy. J stands for jumps here, which is non-negative Borel function on M cross M, which must satisfy two conditions. First, the symmetry. Basically, what I'm discussing today is symmetric processes, for which the question of stochastic completeness is most interesting. And second, it may look as some technical condition, but maybe I write it right away. But in fact, it's very essential one. Supremum in X, integral over M1 minimum with dxy squared jxy d mu y is finite. Or maybe I will write it smaller than or equal to some constant. So I will just show examples a bit later, but maybe I should first notice that this condition will be actually analogous to this one. If we replace 1 here by constant, which nothing changes if we do this, then turns out that analogous of this condition is exactly this one, right? Although it looks more complicated. Right, so these are our given datas, and what shall we do with this? This jump kernel is used to produce the corresponding Dirichlet form, E of f being double integral, 1 put 1/2 here normally, fx minus fy squared jxy d mu x d mu y. Basically, this is analogous to having integral of grad f squared, but of course one replaces here differential operator by the difference operator and add in addition this jump density which relates somehow points x and y, right? So this should be considered as analogous of the Dirichlet form, classical Dirichlet form.
So we can think of this J as a transition matrix, if you like, in a simple.
Yeah, one can think of this. Yeah, it somehow says you the ability of the process that we're going to consider jump from x to y, right? Right. Then one introduces, in a certain way, domain of this form. Basically, we look at functions in L2, so that this quantity is finite. This is initial domain of this form, the maximal one. But then restrict this domain to closure of Lipschitz functions with compact support. Well, I don't go much into details. I just notice the following, that this condition implies that this energy is finite for Lipschitz functions with compact support. If you replace fx minus fy by constant times dxy, which is the case for Lipschitz function, you get exactly d squared here. And if this function has compact support, then one can actually work out minimum of 1 and d squared. One gets finiteness of that. So Lipschitz functions with compact support are dense. Not dense, belong to this domain, and one can actually take their closure in this space and obtain very nice domain of this Dirichlet form, so that this becomes so-called regular Dirichlet form in the sense that allows to define the process, right? So basically, the standard way of defining reversible Markov process is first to define a Dirichlet form with appropriate domain where there are enough continuous functions. And Lipschitz functions here can be used because more than continuous, but they can be used to provide such nice so-called regular Dirichlet form. Anyway, this Dirichlet form induces the process which is of interest for us, a jump process with a jump kernel jxy. Just a bit later I will do this construction on a graph where one can see everything is very simple. Maybe this, but I actually need this general theory in order then to use it on the graphs. Right. So just to give example, not to be too abstract. So in Rn, the well-known and well-investigated jump kernels are the following. It's constant, well, just put 1, no, I put some constant still here, x minus y. Distance, of course, we consider Euclidean one in Rn with Lebesgue measure, right? 2 power n plus some alpha. N being the dimension, alpha is parameter between 0 and 2. And one sees very easily, if one tries to compute this integral in Rn, then it will be finite just because alpha is between 0 and 2. Finiteness at the origin will be given by this, and finiteness at infinity will be given by this inequality. Basically, just to have this condition, it helps to have alpha between 0 and 2. By the way, for those who are familiar with Levy-Hintgen theorem about general structure of Levy processes in Rn, this condition is exactly condition on Levy measure. That Levy measure is exactly jump measure for those processes, and it exactly coincides with this one, this condition for Levy measure. So in particular, this is also one of particular cases of Levy measure. And the process which is induced by this jump kernel is so-called symmetric alpha stable process. Or one says symmetric process of index alpha. And its generator is Laplace operator to power alpha over 2. Assuming that Laplace operator is positive definite, so we have to put minus in front. Just Laplace operator generates Brownian motion, but if we take it to power smaller than 1, it becomes already pseudo-differential operator, and it generates non-local operator, it generates this jump process. So it's a process which well, I cannot draw it because jump process is impossible to draw as a picture. You can perhaps see on computer simulation as a process. It jumps. It has no pieces of continuous trajectories. From every point it can jump to any other point, and probability of jumping far away is restricted by the value of this kernel, right? This x and y somehow jumps here and there, and if a jump kernel has big values at large x and y, it has possibility to go far away, or if not, then it will stay around that somehow. It's jump, so it's difficult to draw it. One can investigate properties of that process, how far it can go, and so on. There are many interesting results in this direction, but the only question that I'm going to ask, in general, not necessarily in this case, if this process is stochastically complete. With the same definition as before, that lifetime is infinity or not. For processes, for Levy processes in Rn, it's known they all stochastically complete. Examples of incomplete process I will show on the graphs. There are very simple ways to see that. But then, before that, I will state a general theorem in this setting, which is kind of analogous of this one. Maybe I put this theorem 1 and put aside here theorem 2.
So these jump processes are continuous time.
Yes, right.
Oh.
Time is continuous, yeah.
So, I mean, are there measurability issues for the ordinates? Because these look horrible. I mean,
Sorry, issues of
measurability for the ordinates for xt, because I mean this thing is going crazy.
no. Normally, they're well. The paths are actually left continuous. Yeah, that's Cadillac paths, right? That's but basically, well, process doesn't have stochastic process doesn't have to be continuous, right? Right. So this one is recent one, is joint work with Zupin Huang, my PhD student, and Jun Masamune was postdoc, I believe it, plus myself. It's very recent, not yet published. So theorem is very simple. Under these assumptions, especially I would like to emphasize assumptions which tells you that there is a certain relation between D and J. We say that distance is adapted to jump kernel or vice versa, jump kernel is adapted to distance if this is true. So under all these conditions, we introduce volume function in the same way. It's measure of every D ball, right? And if for some point x naught, this volume function admits the following estimate, R log R, where now we have to be careful. So far all constants were arbitrary here, but this constant has to be, at least in this theorem, smaller than 1/2. Then the process is stochastically complete. So this also theorem in terms of volume growth, and the reason why the process see the balls is exactly the same as on Riemannian manifold, but the only thing is that relation between D and the process is given in a more complicated way, not just that short way as was here. But nevertheless, distance function is kind of adapted to this process, and one can, well, it happens so that volume test really works in this case. But of course, you see the difference between the borderline volume growth. This is quadratic exponential, and this is just exponential with little addition of log R.
Okay, so I've got so I'm beginning to get a bit of a picture now. Suppose you just have, say, a 2-point metric space. So what happens here is that actually, if you're at a point, you sort of sit there for a while.
And then jump.
And then jump, right. You
Exactly.
don't jump every second.
No, of course, you wait a little bit, yeah. Right,
So somehow this line on the board there, this gives you a jump process with kernel J, hides a certain amount of...
yeah, that's what normally one says, but normally it's weights with exponentially distributed time with expectation what
like 1/c.
something related to yeah. Anyway, it's yeah. In fact, I will show that what you say. It's the example, simplest example of a graph, and I will do the same on general graphs, right? So right. So basically, oh, maybe I should be speeding up. At this moment, we are not sure that this is really sharp borderline. On manifold case, it was known. It was shown that this was sharp theorem. Here, there are certain indications that it might be sharp, although doesn't have to be this constant, right? It may be that there is some borderline constant, so that with this constant, this gives stochastic completeness, and with larger constant, it does not. Maybe I will very briefly explain why I believe that. The point is that on manifold situations, stochastic completeness can be related to analytic problem, completely analytic problem of uniqueness for the heat equation. One could consider heat equation where U is function of Tx, T is positive time, x point on manifold with some initial condition. Suppose initial condition is 0, right? And we want to conclude that u is 0. That is uniqueness problem for the heat equation. Yeah, certainly. It's generally it's not true. Generally it's true only if you assume some restrictions. In Rn, there is well-known Tikhonov class that utx is bounded by more or less the same function as is used here, mod x squared. Then this is the case, right, in this class of solutions. So there are uniqueness classes. Turns out on arbitrary manifold one can write similar uniqueness class in integral form. This pointwise uniqueness class is not true on arbitrary manifold, but if one has write some integral, fix some t in time and space, u squared xt d mu x dt, and if one controls this integral as a function of radius of ball. So this basically tells you how fast can L2 norm of u in balls grow. Then this is the case. Then this is uniqueness class. And this is true on arbitrary manifold regardless of any assumption except for geodesic completeness. And relation between stochastic completeness is as follows. Stochastic completeness is equivalent to uniqueness of Cauchy problem in class of bounded functions. So, but if we replace u by constant by upper bound, assuming u is bounded, then sufficient condition for that would be just boundedness of volume in this way. That's one of the ways of proving this volume test. First to prove uniqueness class and then apply it here. Similar thing one can do for jump processes. One can also relate this to uniqueness problem of Cauchy problem, but of course one has to replace Laplace operator by generator of this process. Right, and turns out that uniqueness class that one gets here is this one, with the same bound for constant c. And this uniqueness class happens to be sharp. For uniqueness class, one constructed example showing that this is really sharp. Constant may be not sharp, but this function is sharp, so there is some borderline constant, right? Unfortunately, this does not mean immediately sharpness of this condition for stochastic completeness, because stochastic completeness is related also to bound of function u. But nevertheless, it's kind of indication that R log R function, which appear in here, is not really just technical one. It's perhaps really essential for jump processes.
So can you say again, what's the relation between this generator L and so the ball is still using the usual Riemannian metric, right? The measure the measure is the invariant measure for L. Okay.
Yeah, I'm mixing up settings. First it was Riemannian setting.
Yeah.
Now I am switching to this setting of jump process, and for the setting of jump process, more strictly speaking, this was not really full setting, some subsetting of that, but nevertheless, well, example when this is sharp is just example of Z. Z, simple random walk on Z. Right? I will come back to that. Right, so that I hope that in fact we've got a sharp theorem here, which gives you stochastic completeness in terms of this volume growth. But now I'm coming to actually the easiest part, which could be stated without much abstract mathematics. Random walks on graphs. Right. Maybe I put it here. Which also can be considered as a very specific example of jump process. Now we consider a graph. I will denote it by gamma. as also set of vertices, also by gamma, a graph which is connected, infinite, and locally finite. Locally finite means that each point has only finite number of neighbors. Something like that. That point X is a neighbors, and so on. Any favorite graph of yours will do. Right? But must be infinite, connected, and locally finite. Right, basically we are going to consider random walk which will jump from one point to a neighboring point, and one of the way of doing this to graph is of course can be considered as metric space. Concerning definition of distance function, I will come back to that at some point, but measure mu and jump kernel J we are going to define. There are various possibilities. Most interesting one is as follows. Mu is the counting measure. That is just number of points of vertices in a set. We consider just set of vertices as M, right? Set of vertices is our space where everything is going on. And mu is counting measure on set of vertices. And by J, I will take the simplest possible one, just indicator of the edge. That is, if x, y are connected by an edge, then 1 and 0 is not. So, which is 1 if x is connected to y and 0 otherwise. That means we allow jumping from x to neighboring point y only, right? What is Dirichlet form? Associated Dirichlet form is sum fx minus fy squared, where summation all xy which are connected by an edge, right? Simplest possible Dirichlet form to define, and the operator, generator of this form, is the following operator. It's Laplace operator, discrete Laplace operator, which I write fy minus fx, where y is connected to x. The summation here only in y. That means we just sum up all the differences, fy minus fx. Maybe I'll make one better picture. This is x, and these are all points y. One takes the difference fy minus fx and sum them up over all edges. This is really analogous of the sum of second derivatives, right?
So I mean, of course, it doesn't make sense if the graph is regular, but
no, graph is not real. Yeah, okay.
You don't divide by the degree.
Right. Yeah, that's the point. I wanted to postpone this a little bit, but those who are familiar with this subject know that typically one divides everything by degree of x. Maybe just to throw this away, I will notice if you do this, then everything slightly changes, and the process that you will obtain will always be stochastically complete. That's consequence of the fact that this normalized Laplace operator, when you normalize by dividing by that, is actually bounded operator, and it's easy to show that whenever operator is bounded, the process is stochastically complete. So I'm going to consider this unnormalized Laplace operator. Or some people call it physical Laplace operator, although I don't know for which reason. But in fact, it looks most like the sum of second derivatives somehow, right? Maybe these are more like first derivative, but nevertheless, it really reminds the classical Laplace operator. Anyway, for this operator, the question of stochastic completeness is really make interesting sense, right? So the process which one obtains in this way is very simple one. Maybe I could just show it here. If the process jumps over points, over vertices, and go each time to neighboring point from x to y. And as I already briefly mentioned, it waits some time here, in time becomes is actually exponentially distributed with expectation of waiting time is 1 by degree of x.
So is that then is that waiting is needed to produce a time reversible thing? Is that the point?
No, time reversible is not related to that. Time reversibility actually sits in symmetry of J. If we consider normalized Laplace operator, waiting time would be 1, right? And this is too long waiting. When you wait that long time, in the end, your lifetime becomes infinity. Right? But if you allow shorter waiting time, and actually main examples that I have in mind with unbounded degrees, graphs which are fastly expanding with large degrees, then this becomes very short waiting time, so it speeds up the movement. And the question, which makes the question of stochastic completeness interesting, or incompleteness interesting. Right. Then, of course, the same question. So what happens with stochastic completeness? For that, we have to return back to distance function and see with respect to which distance function we ask this question, or want to state some result, right? For stochastic completeness, as I said, distance function is not needed, but to state some convenient test, it's still needed. Natural distance function on a graph, I will denote it by rho xy, is so-called the graph distance, or the combinatorial graph distance, which is the minimal number of edges in any path connecting xy. That's distance which takes integer values, 0, 1, 2, 3, and so on, right? So, for example, here, distance between this and this is just 2, because this is the shortest path connecting this, right? Turns out this distance is not adapted. Or maybe we'll see what it means for this to be adapted, right? Integral will become the sum. Minimal with 1 can be removed because distance between neighboring points is at least 1. Then integration should be reduced to only neighboring point because jxy is 1 if and only if x and y are neighboring. If x and y are neighboring, this is 1. So therefore, it's just integral of 1 over all neighboring points. That is exactly degree, right? So the condition, okay, this sum or integral, that will become exactly degree of x, and the condition bounded by constant means bounded degree. And this is most uninteresting case. If degree is bounded, then it's easy to show there is always stochastic completeness, right? So in interesting cases, when unbounded degrees, this adapted condition is not satisfied by the graph distance. So the graph distance is in generally not adapted. But one can modify it by introducing distance that I will define by dxy. Well, it's easy to see how. We have basically divide by square root of degree, right? Okay, I'll write it here. We first define it for neighboring points, x and y, as minimum between 1 by square root of degree x and 1 by square root of degree y. So it makes smaller than 1, right? We make distance smaller than graph distance. But then extend this to arbitrary points by connecting them by paths, sum up those distances along the paths and minimize. Basically, as soon as we know distance between neighboring point, one can extend this to arbitrary points x and y. And this distance, more or less by definition, is adapted one. Adapted one. So in terms of this distance or any other adapted distance, one has this theorem, right? But then the question that I'm going to ask, what can one say in terms of the graph distance? Turns out the answer is very funny and unexpected. Maybe I should erase here.
I'm sorry, is it obvious that what you just defined is a distance?
Yeah, more or less. Okay, to be absolutely correct, one should denote this not by dxy, but some other letter, say sigma xy, and define dxy as infimum of sums of sigma xi plus 1 over all chains connecting x and y. That would be correct. Whenever you do infimum of some sums, it's always a distance. It automatically satisfies the triangle inequality. This theorem gives the answer in terms of volume with respect to graph distance. If measure mu is counting measure of ball with respect to graph distance x naught r is bounded by the following function, r cubed for large r, then graph, or I could say graph, is stochastically complete. So in terms of graph distance, there is entirely different scale of volumes. It's not exponential with anything, not even power, but just r cube. And most interestingly, this cube is sharp, right? R3 plus epsilon already can give stochastic incompleteness. And for that, this theorem was also proved as a consequence actually of this one in the same papers here. But counterexample was known actually before. It is due to Wojciechowski, was recent PhD student of Dojuk. He actually showed very nice example of this type. He calls such graphs anti-trees. The graphs are constructed in the following way. They have levels, level 0, level 1, level 3, 2, and so on. These are just subsets of vertices. There are some number of vertices on each level. Well, maybe I denote levels by S as subsets of set of vertices. The number of vertices so far is not important. Important is how they are connected. Connected, some different every 2 points on neighboring levels are connected. That's the definition of anti-tree. Okay, I think something like that. And so on. And for such anti-trees, Wojciechowski proved exact or necessary and sufficient condition. Stochastic, say, incompleteness, I will write it in this way, incompleteness is equivalent to the following. The sum here, number of vertices in sk plus 1, and here vk being a volume of ball of radius k is actually the sum of s0 plus s1 and so on plus sk. if this series converges, this stochastic incompleteness is equivalent to convergence of that series. In particular, if we take Sk just of order k 2 plus epsilon, which corresponds to Vk volume function of order k 3 plus epsilon, then the series becomes k 3 plus epsilon divided by k 2 plus epsilon squared. And this results in 1 by k 1 plus epsilon, which is convergent, right? Compared to manifold situation, in manifold similar situation can exist just with one Sk in denominator. Here one gets square basically of Sk, and that results in completely different scale of volumes. So that's what the result here, and maybe just one word about the proof. In fact, the theorem is proved by using this abstract theorem by tracing carefully how that volume with respect to volume growth with respect to graph distance results in volume growth with respect to adapted distance. Turns out this cubic volume growth with respect to row distance actually implies with respect to graph distance exponential volume growth with some constant. And this is within reach of this theorem, so we can make conclusion about stochastic completeness, right? Somehow, surprisingly, we didn't find any way of direct proof, despite various efforts, without using adapted distance. Just do something straightforwardly. This R cube seems to be within reach. It's not something, but nevertheless, there is only known proof which goes through this abstract theorem this way. This part is also not that trivial, but it's really more combinatorics. Yeah, right. All right, okay, I finished, must finish here. Thank you very much. I have to.
Any other questions?
Take some of them offline, but well, first of all, the last thing you said is actually surprising. So the completeness, the stochastic completeness.